Welcome to our SCP-140 exploration of the Solar Simulator Lab. You begin the Solar Simulator Lab. It's very similar to the phases of the Moon Lab. There's some instructions that explain a little bit about how the Solar Simulator works. But I'd like to show you as you can watch along, just in case you have some questions. So this is what the Solar Simulator looks like. There's quite a bit of information here. The biggest image that you can see is a picture of a person standing on the ground. As you stand on the ground and you look out towards the horizon, it appears that you're standing on a flat surface. Now we know that the Earth is round. And the only reason it appears flat is because we only see a very tiny amount of the entire gigantic surface of the planet. But nevertheless, if you get very, very close to a sphere and look at a very small part, it's essentially very close to flat. And so that's the approximation that we see in the image, the solar simulator, with the person standing, the sun directly over their head or close to directly over their head, and the compass rose. You can spin things around to get a better view of what's going on. Sometimes you can look from exactly above, or sometimes you can look from dead on, as though you were looking directly at the horizon. You might want to do that at different orientations to see what's going on. And a few things you might notice are some lines, some blue lines, some yellow lines, and some white lines. These different lines correspond to different things that are happening in the sky, and they also correspond to important points in the sky. The blue lines correspond to the location of the north and the south celestial poles, if I spin it around. Whereas the line that spins around the sky and goes beneath and below the horizon, that's the celestial equator. We can also see the line for the sun moving around the planet. That's that yellow line. Now, really what's happening is that our Earth is spinning. The sun is not really moving around the planet, but instead, as the day goes on, the sun changes in its position in the sky as we on the Earth experience a turning planet. And we can see that happen if we just run the animation. As we run the animation, the sun travels along that yellow line and spins back up again, and then we have the next day. The next question you might ask yourself then is, what does this white line correspond to? Well, the white line corresponds to the location of the sun as the year goes on. As the year goes on, the sun will be in different parts of the sky from day to day. This is actually due to the changing of the seasons. So if you wait long enough through this animation that we're looking at, you can actually see how the seasons change. Now, we start our observations at a location that's pretty close to where New York City is. You can see our observer latitude is 40.8 degrees north. You can change where you are located on the planet if you want. And you can see that those paths that the sun is taking through the sky will change accordingly. I'm going to stop the animation now and reset. The reset animation always starts at the 27th of May, and it starts at a time of 12 noon. Now you'll notice that the clock we have below is a 24-hour clock, slightly different than the clocks you might be used to. So it might take some getting used to in using that. But you can move the hands of the clock, the minute hands, or you can move the hour hands, and you can see how things will change in the sky depending on what time of day it is. If you'd prefer to just enter the time of day, you can also do that as well. Or you can click on the little clock symbol and choose the appropriate time of day that you would like. Sometimes that's better to do than running the animation. I'll reset this again to the starting point. Many questions that you'll have in the exploration will ask you to start at that starting point and press reset. As I said, you can also change where you're located on the Earth. I can move the observer's latitude either north or south by clicking on these arrows and moving it across the planet. And you might think about how those different changes may occur. Of course, you can also enter in a change of the observer latitude here. There are a number of other settings that you can indicate, and you can change the animation as well. The animation right now basically runs the clock as you would see it over the course of the day. You could run that day over and over again. That's what loop day means. Or you can step day by day to see how the sun might change over the course of the year at the same time. Let's say if we did it at noon and we'd step day by day, we would see that the sun is changing position ever so slightly according to the changing white line that we see, the path that the sun is taking over the course of the year. I'll stop that animation now, and we'll do another reset. Now, one of the things that you'll want to take note of is the information that you have here. The information will first indicate some of the things that you already know about the simulation. Where you're located on the planet, that is your latitude, 40.8 degrees north is where I'm located. What day the observations were taken, this is May 27th, and what time, 12 o'clock, 12 noon. This will be in military time, so it'll start at 0 and go all the way to 24 hours. There are also some advanced pieces of information. One piece of information that's advanced is something called the hour angle of the sun. This is using the sky as a clock, where we say that 0 hours is right as high as the sun can get. As the sun passes the meridian, that is the line that extends between north and south, that would be a line of 0 hours. Since we're at noon, the sun is very close to that. It's not exactly there, and there's some explanation for that in your text. You'll have to read about the equation of time. There's another piece of information, which is the sidereal time. This is the time that is associated with the location that the sky is showing right now. It's a little bit more complicated because we don't often use the sky as a clock anymore. In the past, people did quite a bit, and so sidereal time was important. We don't ask any questions about sidereal time in the laboratory, but if you're interested in it, your textbook does explain exactly what that is. And as I said, there's also an equation of time that's indicated. If you'd like to learn more about that, there is a question in the investigation that asks you about this, and it gives you some information there. You can also turn on something called the analemma. And if I do that, this really just shows you the different positions the sun will have over the course of the year at this time. It will follow this path over the course of the year. This is another way of tracking that intersection between the yellow and the white lines. Finally, there are 4 other pieces of information which are very useful, and I suggest that you investigate those and learn about them very carefully. The first one is called the sun's altitude. That's telling me how high above the horizon the sun is, 70.5 degrees. If the sun was directly overhead, it would be at 90 degrees. But because we are not at a position where we can see the sun directly overhead, it's pretty high in the sky, but not directly over our head, 70.5 degrees. Another piece of information that we have is something called the azimuth of the sun. This is telling me how far in the east-west direction the sun is pointing. Right now, it's a little bit ambiguous because we're at 12 noon. So I'm going to change the time to something like, well, let's change it to about this time here, 9 o'clock. And you can see that the azimuth of the sun is listed at about 109 degrees. This is really telling me along a compass where the sun is pointed. Compass starts with 0 degrees being exactly at north, and 180 degrees being exactly at south. And going between 0 and 180 degrees is going through the eastern part of the sky, and going between 180 degrees almost to 360 degrees is the western part. So if I see that the azimuth is at 109 degrees, I realize that I'm in the eastern part of the sky, a little bit towards the south. That's where the sun would appear to be located, according to my observations. There's another bit of information here, which is the right ascension of the sun. This is the location that the sun has on the celestial sphere. We demarcate the celestial sphere in things that correspond to roughly longitude and latitude here on our planet, but our imaginary lines we make on the sphere we see above our heads, we call the celestial sphere of the sky. And the right ascension corresponds to roughly longitude. And in this case, we actually measure it in hours because it takes the sun 24 hours to go across the entire sky. And so as it goes across the sky, it's demarcating different hours. And so this is the 4th hour of the sky. Now this position on the sky never changes night to night. So there has to be a particular day when we declare that 0 hour is exactly at noon, for example. And that day is usually taken to be the spring equinox, about March 21st. The other piece of information that we have here is something called the sun's declination, which is something you may have explored on problem set 1 already. The declination of the sun is according to the lines that match up to the lines of latitude on the Earth, but they're the lines of declination on the sky. And that tells you how close the sun is to the celestial equator or to the north celestial pole. And here it's at 21.1 degrees, which means that it's only 20 degrees away from the celestial equator, but it's almost 70 degrees away from the north celestial pole. Those pieces of information may be very useful for you. For example, you may be asked when the sun sets or when it rises. And in those cases, you know that you'll want to look for a very low altitude, an altitude that's close to 0 degrees. Or you may be interested in finding out when the sun is at its highest point. In those cases, you'll want to look for when the sun reaches the highest altitude, or when it passes the north-south line. In the northern hemisphere, that would be when it passes 180 degrees because the sun moves to the south. And in the southern hemisphere, that would be when it passes between 360 and 0 degrees, which are the same measurement with it, because the sun is always in the north. You'll be moving yourself around the planet, trying to explore these different things, making these measurements, seeing what times you can find, and seeing how the sun might move if you were in different places in the sky. This is the way this lab works. So I hope this walkthrough was useful. I hope it was interesting. And I hope it helps you solve some of the problems associated with the solar simulator. Enjoy your explorations, and we'll talk to you again very soon.